So currently I am traveling abroad, but I will be taking 2 classes per week, and they will be on Wednesday and some other day, maybe Sunday or Monday, Monday maybe. And until I get back to Bangladesh, which will be the beginning of July. And my experience with online classes is that you can cover more in online classes, okay? So I think that for now, having 2 classes per week would suffice. But when I get to Bangladesh, we might have to switch 2 in-person classes and 1 online class. Okay? So I haven't posted the um, syllabus yet, but let me just give you a rough outline of what will be covered in this course. And please interrupt me anytime if you have any questions, okay? So first is that we are going to start where we left off in quantum mechanics 1. We're going to do the simple harmonic oscillator. And we're going to do it in 2 different ways. Okay? And after that, I'm going to discuss kind of a review, the general, after that, we are going to do the pictures, the Schrodinger picture, the Heisenberg picture, and we are going to do something called the interaction picture. So these are different ways of looking at quantum mechanics, and it's very, very useful. So number 3 is we will then do a review of the fundamental postulate. Okay. And then that's number 3. And then we are going to do what are density matrices. And in this, we are going to introduce the Dirac notation. After density matrices, we are going to do, Schrodinger's equation in higher dimensions, say in 2D and 3D, okay? And then we're going to do rotations and rotations, and then translations, rotations and translations. Like if I rotate or translate a quantum system, how does it affect the Hilbert space? How does it affect the space of states? Okay. And then we're going to have orbital, how to represent orbital and spin angular momentum. Okay. And over here, there will be the representation theory of spin. Representation theory of the SU2 group. This is the group of generalization of the group of rotations in 3 dimensions. And after that, we are going to look at the central force potential into central force potential with 2 particles. So this is the setting up for the hydrogen atom, and then we're going to solve hydrogen atom. Okay. So it's a tall order. It's a pretty long list. So we better start now. And I hope to give you around 6 or 7 assignments and 6 to 7 quizzes, n-1 quizzes and assignments will be counted. And there will be sharp deadlines. Sharp deadlines for assignments. Okay. The other thing is that there will be no makeup midterms. Makeup mids, quizzes, etc. If you miss your midterm, you have to pay 3,000 taka fine at BRAC University to make it up. Okay, so if you, I am not going to ask you, tell you this again, if you send me a request saying that, sir, আমার এই কারণে ওই কারণে আমি midterm দিতে পারি নাই, আমি কি পরশুদিন midterm দিতে পারি কিনা, I will not even answer your question. You will have to go through the official channel. Okay. Similarly for finals. All right. Are there any questions? Okay. Okay, there are no questions, so let us start. Sorry. It's a really awful.
Sir, the mark distributions will be same like QM1?
Yeah, it'll be the same. I will announce that soon.
Sir,
It's the stamp. Sorry?
স্যার উপরে যে স্যার টপিকের লিস্টগুলো দেওয়া ছিল স্যার একটু স্যার আরেকবার নেওয়া যাবে?
Yeah, take a screenshot. All right.
Sir, thank you, sir.
All right. So first of all, why are we interested in the harmonic oscillator? Why the harmonic oscillator? It turns out the harmonic oscillator is one of the most important problems there is. Okay. I don't know what happened to color yet. So it's one of the important problems there is. And the reason is that if you have some sort of potential, so if you have a potential, with a minima, with a minimum or minima with, say, ekadhik minimum, then the low energy excitations are given by the excitations of the harmonic oscillator. So that's one reason. That's reason number one. Number two is that when we go and actually deal with many body systems and many when we deal with many degrees of freedom, by many I mean where the number of particles is not fixed, and such things happen in high energy physics, where because of relativity, energy can be turned into mass. So particle can get created from energy and it can get destroyed, stuff like that. We need a generalization of quantum mechanics known as quantum field theory. In quantum field theory, in its 0th order approximation, can be thought of is a collection of an infinite number of quantum simple harmonic oscillators. Okay. So the intuition that we glean from the simple harmonic oscillator is important when we go and do more complicated real world physics problems using quantum mechanics. So these two are the main motivation. It has been said that the modern quantum field theory is essentially the application of simple harmonic oscillator to more and more sophisticated settings. Okay. So let me just give you what I mean by the first reason. So suppose you have a potential like this, and so you can, so this is a local minimum, and this is a global minimum. And suppose that you are just looking at an energy which is kind of like this, okay? Or you're looking at an energy which is over here, and you are not looking at these states, but just the oscillations around this point or this point. So so let's take this, x naught is a minimum. Then what we can say is that, well, we can expand the potential around V x naught at V of x naught plus x minus x naught dV by d of x evaluated at x equals to x naught plus x minus x naught squared by factorial of 2 d squared v dx squared x equals to x naught and higher order term. So this is just a Taylor expansion. But x naught is a minima. So what does that mean? That means that at x naught, the v is maximized, right? So around the minimum, the potential is given by v of x naught, and this is a constant, right? This is a constant plus a term which is half times, this is another constant, but this is not, this is a positive negative constant. This thing, is that a constant positive or negative? So
is it
negative?
Negative. নেগেটিভ কেন?
Sir,
So
this is different.
we have an extremum
Uh,
at critical distance.
একজন বলো, যে নেগেটিভ বলছো সে বলো।
Sir, I think it's because we have an extremum at x equals x naught.
রাইট, সো যদি মিনিমাম হয় তখন কি নেগেটিভ হয় নাকি পজিটিভ হয় সেকেন্ড ডেরিভেটিভ?
Positive, sir.
সো এটা কি পজিটিভ নাকি নেগেটিভ?
Sir, can I see the figure?
না না, মিনিমামে হইলে সেকেন্ড ডেরিভেটিভ কি হয়? পজিটিভ হয় নাকি নেগেটিভ
Sir,
হয়?
positive.
হ্যাঁ, সো ইউর আনসার শুড বি পজিটিভ, নট নেগেটিভ।
Yes, sir.
The figure is here. So here it's a positive constant k times x minus x naught squared, where k is this constant d squared d dx squared evaluated at the global minimum, right? So you have seen this sort of potential when you were doing Hooke's law. So this is just a constant. So we know that we can always subtract a constant from, subtract a constant from a potential. So now we have a potential, and the leading order, it's just this, right? Where psi is just x minus x naught, right? So this is our potential, and this is the potential of a simple harmonic oscillator. So what is happening here geometrically? Near the minimum, the potential is approximated by a quadratic potential, right? So for small oscillations, I'm exaggerating, for small oscillations, we can approximate the oscillations as if they are happening in a quadratic potential. All right, so this is the justification number one. Is that clear? So an example of this, an application of this is small atomic oscillations in solids, right? So solid ki hoy? We have some sort of lattice, right? The atoms are arranged in some sort of lattice. I've written it as a square lattice, but it can be more complicated. And what's happening is that they are interacting with some sort of potential force. And the force is, I don't know what, some maybe van der Waals or something like this. And the force looks something like that, the potential. So for small oscillations, we are only interested in this region, right? So if this is R naught, so this is going to be the distance between the atoms. But because of thermal energy or energy that it's absorbing from the environment, these will have small oscillations. They will have oscillations like that, right? And these oscillations, if they're small, you can approximate them by just the oscillation, just the part of the potential which is around the minimum. And that is going to be a quadratic potential, okay? So this is a very extremely important application of the harmonic oscillator. All right. As I said, if there are questions, please interrupt me. Okay. It's okay not to understand something. Okay. But it's not okay to not understand something and be silent. Okay, so now we want to concentrate on the Hamiltonian of the system and solve it. So the Hamiltonian first we look at the classical Hamiltonian. So the Hamiltonian of the simple harmonic oscillator is that it's a particle, so it has some kinetic energy, and the potential energy, as we said, is going to be this, where K is a real number, positive real number. Okay. So let me sketch the potential. So one thing you have to always do is that whenever you see a function in physics, you should always try to sketch that function. If it's simple enough, something I saw and I was shocked by in the previous course is that many of you were not able to sketch very simple functions, okay? And so that's something you need to address. So the potential here, it's going to be a bounded, a potential that will, the particle will be bounded. So it'll be something like this. Sorry, it's not a very good sketch. It's also not a very good sketch. But why is the motion bounded? Why is the particle bounded? Can someone tell me? The motion will be bounded. But why? While you think about it, I'm going to get some water. I'll be back. Okay. Yeah, please.
এখানে তো স্যার নেগেটিভ এনার্জি তো পসিবল না।
Yeah, নেগেটিভ এনার্জি সাথে বাউন্ডের কোনো মানে ডিরেক্ট সম্পর্ক নাই।
But there is a minimum energy that being implied by the Hamiltonian.
না, বাউন্ডেড বলতে কি, এই যে আব্দুল্লাহ আল ওমর গালিব বলেছে, the particle will move through back and forth. আচ্ছা, the particle will so that is the right answer, is that suppose you take, so think of it as a classical system, okay? Whether something is bounded or not, we think in terms of, so classical system to the hoy, suppose you take some energy, total energy like that, E. Okay, so the particle will have turning points, right? This will be a turning point, x1, and this will be another classical turning point, x2, right? And the particle cannot move outside this point x1 or x2. Why? If it moves over here, is it possible for the classical particle to move beyond less than x1 and more than x2? কি হবে? তাদের টোটাল এনার্জি, তার এনার্জি কনজারভেশন থেকে কি বলবে?
ওই ক্ষেত্রে এনার্জি কনজারভেশন ভায়োলেট করবে।
না, এনার্জি কনজারভেশন ভায়োলেট না করে, যদি না করে, আমি বলতেছি এনার্জি কনজারভেশন ভ্যালু হচ্ছে না, তখন কি হবে?
স্যার মার্বেলের মতো মানে হলো বাটির মধ্যে ঘুরতেই থাকবে আর হচ্ছে
না, সেটা বুঝতে
ওইখানে
পারছি, কিন্তু আমি 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 ম্যাথমেটিক্যালি বলতেছি এখানে এইটাই তো আমার এনার্জি, এইটাই তো আমার
স্যার
এনার্জি।
মানে ওই রেঞ্জের মধ্যে আটকা পড়ে থাকবে আর ওইখানে
হ্যাঁ,
হলো
ওই
oscillate
রেঞ্জের
করবে।
বাইরে যদি আমি যদি ফোর্স করি এক্স এর ভ্যালু, ম্যাথমেটিক্যালি বলতেছি, আমি যদি এক্স এর ভ্যালু ফোর্স করি ওই রেঞ্জের বাইরে, তখন কি হবে? হোয়াট উইল গো রং উইথ দিস? আচ্ছা, এই পয়েন্টে এটার কাইনেটিক এনার্জি কত বলো? এই পয়েন্টে
জিরো।
0। আর এই পয়েন্টে কাইনেটিক এনার্জি, পোটেনশিয়াল এনার্জি কত?
ম্যাক্সিমাম।
হুম, তাহলে এই পয়েন্টে টোটাল এনার্জির সাথে পোটেনশিয়াল এনার্জি সম্পর্ক কি?
অসিলেশনের মতো।
না, এই পয়েন্টের কথা বলছি, এই পয়েন্টে টোটাল এনার্জি আর টোটাল এনার্জির সাথে পোটেনশিয়াল এনার্জি সম্পর্ক কি? তুমি তুমি
একই
বলতেছো,
মানে
তুমি, হ্যাঁ,
টোটাল
একই,
এনার্জি ইকুয়াল টু
পোটেনশিয়াল এনার্জি,
মানে নিচের পয়েন্টের টোটাল এনার্জি কাইনেটিক এনার্জি ইকুয়াল টু হলো x1 ইসের পোটেনশিয়াল এনার্জি।
রাইট। তো এইখানে হচ্ছে গিয়ে কাইনেটিক এনার্জি ভ্যালু হচ্ছে গিয়ে ই, রাইট, কারণ পোটেনশিয়াল এনার্জি। আর এইখানে কাইনেটিক এনার্জির ভ্যালু হচ্ছে 0, ই হচ্ছে পজিটিভ। তাহলে তুমি যখন এই দিক থেকে এই দিকে যাবা, তুমি যখন এইখানে যাবা, কাইনেটিক এনার্জি কি হবে ম্যাথমেটিক্যালি, যদি ই আমি কনস্ট্যান্ট রাখি?
নেগেটিভ।
হ্যাঁ, নেগেটিভ। কাইনেটিক এনার্জি কি নেগেটিভ হইতে পারে?
না
এইটা যদি নেগেটিভ হইতে হয় তাহলে কি মোমেন্টামের কি হতে হবে?
স্যার হলো হলো ইমাজিনারি।
ইমাজিনারি। সো এটা তো হইতে পারে না, ঠিক না? মোমেন্টাম তো আর গাঞ্জা গুঞ্জা খায়া ইমাজিনারি হয়ে যায় না, ঠিক না?
That's it.
হ্যাঁ, সো এই কারণে দেখো যে এইটা বাউন্ডেড, তার কারণে যে টার্নিং পয়েন্টস গুলি, দুইটা টার্নিং পয়েন্ট আছে, এবং এটার ক্লাসিক্যাল পার্টিকেলের মোশন মাস্ট বি বাউন্ডেড, আনবাউন্ডেড না। আমি আনবাউন্ডেড মোশনের একটা এক্সাম্পল দেই। ধরো এরকম একটা পোটেনশিয়াল যদি আমাদের থাকতো, হ্যাঁ, তো এটা একটা পোটেনশিয়াল, এটা ভি। এই পোটেনশিয়ালে যদি আমার এনার্জি এটা হতো, তাহলে আমার একটা টার্নিং পয়েন্ট থাকতেছে এখানে x1, রাইট? সেইখানে একটা পার্টিকেল ইনফিনিটি থেকে এসে, সেইখানে এসে তার কাইনেটিক এনার্জি কমে কমে এখানে 0 হয়ে আবার সে ফিরে যেতে পারতো, ঠিক না? তো এই ক্ষেত্রে পার্টিকেলটার মোশন কি বাউন্ডেড ইন আ ফাইনাইট রিজন? Nine. Yes, it's not. So এটা হচ্ছে গিয়ে example of an unbounded motion. Okay. So oscillator, simple harmonic oscillator ক্ষেত্রে আমরা পুরোপুরি bounded একটা সিস্টেম নিচ্ছি। ওকে, এটা সব। এবং আমরা দেখছিলাম যে আমরা কিছু সিম্পল সিস্টেম দেখছিলাম, এবং পার্টিকেল ইন আ ইনফিনিট পোটেনশিয়াল ওয়েল, এবং অলসো ইন আ ফাইনাইট পোটেনশিয়াল ওয়েল, ওটার এনার্জি যদি টপ এনার্জি থেকে ছোট হয়, তাহলে ওখানে ডিসক্রিট কোয়ান্টাইজ এনার্জি আইগেন স্টেটস থাকে। তো এখানেও আমরা এক্সপেক্ট করবো কোয়ান্টাইজ এনার্জি আইগেন স্টেটস, রাইট? এবং আর্গুমেন্টটা মনে আছে কিনা জানি না, তুমি কোয়ান্টাম ওয়ান থেকে আর্গুমেন্টটাকে ই করে রাখো। ওয়াই ইটস কোয়ান্টাইজ, তার কারণ হচ্ছে গিয়ে from the fact that the wave function has to go to 0 as x goes to plus or minus infinity. যার ফলে wave function গুলি over constrained থাকে। The solution of Schrodinger's equation becomes over constrained, and therefore they cannot be solved for arbitrary values of energy eigenvalues. Okay, so I'm not going to repeat that because this was covered and discussed in quantum mechanics 1. Okay, Ryan is saying, sir, in quantum mechanics 1, we studied quantum tunneling. Is that an example of a state where it goes beyond bounded state? Yes, that's a very good question. So we didn't really study quantum, no, yeah, we studied quantum tunneling. No, that's still an unbounded, yeah. But what you're saying is something like this. We had this thing, and we had this thing, and we had this thing. And the energy was something like this, okay? So here, energy is, this is a classical turning point. So particle coming in this direction will turn back and go back to infinity. So that's still an unbounded motion, okay? However, something that we haven't discussed, but suppose you have a potential which was like this. Okay. And if the energy is like that, then there will be particles which will be coming from infinity and going back, coming in from infinity and going back. So those are unbounded motion. But there could be particles here which are bounded. So in that case, this bounded particle, depending on how thick the wall is, can actually quantum tunnel outside. Okay, in that case, bounded motion can become unbounded motion by quantum tunneling. And that's something that we will study in quantum mechanics 3, because that is related to what we call, this is basically related to radioactive decay, okay? All right, very good question. All right, so I want to get back to my potential. So again, let me write the Hamiltonian. So first, look at the classical solutions. Okay. So you can, from this Hamiltonian, you can derive an equation of motion with Newton's equation, right? Newton's equation কি বলে আমাদের? M আমাদের বলে যে P dot, right, is equal to F, right? Or minus d by dx, right? Isn't that Newton's equation?
Yes, sir.
All right, exactly. So if I do this, then what is P dot in this case? P dot is mx double dot, right? The rate of change, the acceleration times mass. And this is going to be minus dv by dx. So this is, if I take the derivative of this, I will get minus k of x, right? So my differential equation will be minus k over m of x, right? So, so this means that because of this is a positive constant with a negative sign, with a minus sign in front. So that means that we are going to have oscillating solutions. If this sign was positive, then we would have decaying or exponential solutions, right? So we can say a general solution of this, if I take it to be real, it doesn't have to be real. It's going to be some amplitude, a constant of integration, times cosine of a constant omega of t plus phi, where phi is another integration constant. But for this to be a solution to that equation, omega has to be equal to K over M. Okay, and you can verify that. Okay, just plug this guy into this equation and you will find this. All right. So, and omega has the dimension of inverse time. Okay, also verify that. Another thing I noticed in my quantum mechanics course is that something that I wanted you to learn, but you still haven't learned it, is about dimensional analysis. So whenever you see something, you have to ask yourself, what is the dimension of this quantity? Okay? It'll happen over time, so there's no rush, but omega has. So to get omega's dimension, you have to know the dimension of K, right? And the dimension of K is given by del V by del X, right? So this has dimension of energy, and this has dimension of length, right? So you work from there. All right. So, but what I wanted to show is that this is basically our classical solution. So now we move to quantum mechanics, and in quantum mechanics, we are going to solve the time-independent Schrodinger equation. The time-independent Schrodinger equation, because we know that if we solve the time-independent Schrodinger equation, the time-dependent Schrodinger equation is automatically solved. So what is the time-independent Schrodinger equation? It's just the eigenvalue equation. The Hamiltonian acting on my state psi, and the Hamiltonian is real, so it's just going to be a Hermitian. So it's going to, there is no complex number in the Hamiltonian, so this is a real equation. So what is the Hamiltonian? Well, the Hamiltonian is minus h squared by 2m d squared by dx squared psi of x. So this is the p squared by 2m acting on psi term. And then we have a potential energy term, which is going to be V of x, and then psi of x, and this is going to be equal to E of psi of x. So this is the Schrodinger equation. All right. And we can rewrite this by multiplying by the inverse of this thing, because that's just a non-zero constant. So then we get plus, and we can bring this guy on this side. So it had a minus sign, but because we are multiplying with something negative, it will become plus. So we get 2m by h bar squared. Here we have E, the energy, minus half kx squared. I'm putting in the explicit value of the potential here, acting on psi. So this is my Schrodinger's equation, time-independent Schrodinger equation, which we want to solve today. Okay, so this is doesn't look obvious, but the solution is going to be because of this. This is not a constant. All right, so we have a few constants here, k, m, h bar. So we are going to massage the variable so that we just have the barest minimum. So eventually it'll become clear, but we are going to measure the energy in units of E naught, where E naught is given by half h bar omega. Okay, so we're going to measure. So then the energy will be some multiple of E naught. So some multiple lambda times E naught. So we are going to use this to eliminate E from this equation. The other thing is that the amplitude, the oscillations will be measured in terms of the class of A, which is the amplitude. So we are going to see that this has a dimension of length. Well, this is actually the classical amplitude, right? If I think of this as, let me see. Yeah. So why is this the classical amplitude? Because if I go back to my classical solution, right? The total energy that is given by half Ka squared, right? Because when the particle has its maximum oscillation, that's when the kinetic energy is zero, and the potential energy is the total energy, and x is equal to A, right? At that point. And so what I can do is that I can say, okay, I've decided that I'm going to, if this is going to be equal to, say, the amplitude of the minimum energy, then it's half h bar omega. Then from there, we say that A is going to be okay. We also know what K is. K is given by this, so K is m omega squared, right? K is m omega squared, and here's A squared, and here we've got h bar omega. So we get 1 omega canceling out. So we have A, which is h bar by m of omega square root. Okay, so what we are doing here is that this is the amplitude. This is the amplitude of a classical oscillator, say with energy E naught. So then what we're going to do is that we're going to measure our displacement in terms of A. So we define a new displacement x prime, which is given by this. So you see, both x and A, they have dimensions of length. So our new x prime, this new length, has no dimension. Okay, it's a dimensionless unit of length. So similarly, if I look at here, this has dimension of energy, this has dimension of energy, therefore this has dimension. This is dimensionless. So now we rewrite Schrodinger's equation in terms of these new variables. And what we find is that we get m omega by h bar times d squared psi dx prime squared plus lambda minus x prime squared psi is equal to 0. And because this is just a non-zero constant, we can divide it, and then we get d squared psi dx prime squared plus lambda minus x prime squared psi is equals to 0. So this is, see, this is why did I do this? This is the same equation as before, but I'm using units in which things look less cluttered, okay? Once we have solved this equation, we are going to put back our original variables, okay? However, now, there is no x here, it's only x prime. So we rewrite this, we just drop the prime. Okay, but we are just doing it for convenience, okay? So this is the equation that we want to solve. All right? Are there any questions?
So why do you want x prime to be dimensionless?
Sorry, can you repeat?
So why do you want x prime to be dimensionless?
Oh, we just got rid of all these constants. It's like মানে অনেক সময় তুমি যখন হাই এনার্জি ফিজিক্স পড়বা, হাই এনার্জি ফিজিক্স এইচ বার, স্পিড অফ লাইট, এগুলি সব হচ্ছে কি 1 করে দেয়। তখন হয় কি যে ইকুয়েশনগুলি look less cluttered. এবং the interesting thing is that by doing dimensional analysis, you can always put back those constants, okay? So, for example, ধরো যে আমি এখানে উত্তর পাইলাম একটা, যে আমার ল্যামডা হচ্ছে কি 3, ওকে? তার মানে এটা এনার্জি আমি জানি। সো আমার ডিমেনশন, তার মানে ই হবে, যদি আমি এনার্জি এই হবে ই টাইমস হাফ এইচ বার, রাইট? কারণ আমি জানি যে আমার এই ইউনিটে আমি, দিস উইল বি দ্য ইউনিট, ওকে? সো ওই রকম আর কি। ধরো যে একটা লেন্থ পাইলাম 5, তখন আসলে আমার তখন লেন্থ হবে 5 টাইমস এ, ওকে? সো মানে আমি হচ্ছে গিয়ে ধরো যে আমরা তো ফিট মিটার এগুলি ইউজ করি, ঠিক না? কিন্তু তার বদলে যদি আমি বলি যে না, আমি আসলে হাত ইউজ করবো, আমার 5 লিখে নিতে হবে, তুমি যদি জানো। অত মিটারেরও তো তোমার, আমি যদি জানি আমি কোন ইউনিট ইউজ করতেছি, তখন তো আমার ওইটা স্পেসিফাই করতে হচ্ছে, ঠিক না? ওকে, just to make this equation look nicer, nothing else. We could have done it without, but all right. Any other questions? Okay, so let's look at this equation. So this is basically, if I were to write it in the traditional way, it would be minus d squared dx squared plus the potential is this x squared, and this is lambda of psi. Okay, so this has the form of an operator O, a Hermitian operator, we shall see, acting on psi, giving me lambda of psi. So the lambda are the eigenvalues, okay? I should really write this as small h, because this is actually the Hamiltonian in the rescaled coordinates, rescaled variables. Okay, so this is an operator, and this is the eigenvalue of the operator. All right. Okay, so let's first prove that the energy is positive. The positivity of the energy. Okay, and for this, because I'm going to switch back to my traditional variables. Okay. So now let's take, so for example, we know that for Hermitian operators, if I have this, so for any operator, we can write this as this, right? Right, but for Hermitian operator, I can write this as this, right? So now let's take a state psi, whatever, any state, and look at the expectation value of the Hamiltonian in that state. So what are we doing? We are measuring this thing. Psi h, so let me put, I'm going to forget the hats. Okay, so this is what we want to see. So here, Hamilton, we can write, this has two terms, right? So we can write this as psi comma p squared by 2m plus half kx squared psi. But this is linear, and this is a linear operator. So we can write this as 1 over 2m psi p squared acting on psi plus half of k psi x squared acting on psi. Right? Any, I think this should be straightforward. So what we can do is that there are two operators, right? We can peel one of the operators, and it's a Hermitian operator. So what we can say is that, okay, we just peel one of the p's and bring it over here, so you get p dagger of psi, and here we have p of psi. Similarly, over here we have half of k, x dagger of psi, x of psi. But p and x are Hermitian operators, so we can get rid of the dagger here. And over here we have x, just x of psi and x of psi. Now here we have something very remarkable. So if you define p acting on psi to be some state phi, and x acting on psi to be some other state, say zeta, then the expectation value of psi becomes 1 over 2m, the inner product of psi with itself, or the norm of phi, so phi, and plus another positive constant times the norm of phi. Do you agree? Norm of zeta, exactly. গালিব বলে যে স্যার কোয়ান্টাম কেমিস্ট্রিতে ডিরাক সুইচ করবে না, কি এর মধ্যে কি পড়াইতেছি, আর এর মধ্যে আবার এসব কি? ডিরাক কি তোমার দাদা লাগছে নাকি? হ্যাঁ, ডিরাক করতেছো, আগে কোয়ান্টাম মেকানিক্স বুঝো, তারপর ডিরাকের কথা বলো। Okay, any other questions? Okay, so this is a very রাইন আবার হাসছে, তোমারও মাইট দিতে হবে। So look at this, that this is a positive constant, right? This is a positive constant. This is positive and this is positive, right? কারণ আমরা জানি যে the definition of norm is this is positive semi-definite if this is 0, then this means that phi is 0. Okay. তো তার মানে কি? তার মানে আমরা বলতে পারি the Hamiltonian of this is positive definite. Right? বলতে পারি না আমরা? So this is an important thing that আমাদের the form of the Hamiltonian guarantees that we have a positive definite expectation value. Okay, so what is the expectation value of the Hamiltonian? Well, it's basically, according to quantum mechanics, all the energy eigenvalues of the Hamiltonian times the probability that your state is in that energy eigenvalue, right? This is the definition of expectation value. So eta jodi positive definite hoy, so these are probabilities, so they are all positive definite. Okay. So এই সামটা যদি পজিটিভ হয় তার মানে কি এরা সবাই পজিটিভ হতে হবে, রাইট? Right? Do you believe that? Okay, Dalit believes it. So তার মানে কি? তার মানে the energy is positive definite, right? The energy eigenvalues are positive definite. Okay. And there's an assumption here. And the assumption is that this is the probability distribution of an arbitrary state psi. So in some sense, the probabilities cannot be too finely tuned. Right. So for example, যদি এরকম হইতো যে probability ধরো একটা energy state আছে say EA, which is minus alpha, where alpha is a constant, and another energy state EB, which is plus alpha. And the probability of P, say A, is say, I don't know, some small number beta, and probability of PB is some number minus beta, right? So then if I have alpha times beta plus alpha times minus beta, sorry, probability to negative হতে পারে না positive, একই probability হতে হবে, হ্যাঁ? So তাহলে this can be 0, right? But that means that the probabilities have to be finely tuned. Okay. So that's one way of thinking about it. But another way of thinking about it, which is more straightforward, is to take psi to be an eigenstate. So that in that case, H is just going to give you the eigenvalue. Okay, eigenvalue. And in that case, the single eigenvalue. So you can take each of these states to be a single eigenvector. If you take each of these states to be single eigenvector, there's only one term in the sum. And therefore, each eigenvector separately is positive definite, okay? Okay, so now that we have shown the positivity, let us get back to the differential equation. So what is a differential equation? It's psi double prime plus lambda minus x squared psi of 0, where psi prime means d psi by dx, and psi double prime obviously is d psi prime by dx. Okay, so we want to solve this. So before we solve this, let's solve this asymptotically. So what is asymptotic analysis? Means that we are going to take x to infinity and see what we get. So when x becomes large, this term is going to be small, right? So for large x, the differential equation becomes approximately this, okay? Now this is actually quite easy to solve. And the solution of this is given by psi, some constant, x to the power n, then e to the power plus minus half x squared, okay? Somebody is not muted. Can you please mute yourself? Lail, can you mute yourself? Okay. I have taken the liberty of muting you, sorry. So I'm claiming that this is a solution to this equation, all right? So let's see if that is the case. So let's take psi prime. Psi prime is Cn x to the power n minus 1, e to the power plus minus half of x squared. So that's the first term. And then we are going to have a second term, which is going to be plus minus Cxn. But এখান থেকে এই জিনিসটা নামবে। So ওখান থেকে নেমে কি হবে? Half আসবে একটা। So let me just do এখানে আনি। So এখান থেকে একটা হাফ নামবে, তারপর এইটার ডেরিভেটিভ হবে 2 of x, তারপরে e to the power plus minus half of x squared. এই 2 কাটা যাবে, তো psi prime হবে Cn xn minus 1 e plus minus half x squared plus minus c x n plus 1 e plus minus half x squared, right? So that is psi prime, but we need psi double prime for this, so we need to take its derivative again. So if I do this, I get c here, n, and then its derivative gives me n minus 1, and then we have x n minus 2, and here we have my e to the power plus minus half x squared. And then we have the derivative of this thing, and here we are going to get plus minus as before. And again, we are going to get here cx, এখানে যেমন x to the power n, x to the power n plus 1 হলো, এখানে x to the power n minus 1 will become x to the power n, একইভাবে, এবং there will be a with a factor of n. Okay. And then, which was there before, right? So I should probably write the Cn x to the power n e plus minus half x squared, right? So this takes care of the first term. Now we move on to the second term. So in the second term, we have plus minus c, and then we have n plus 1, and then x to the power n, e to the power plus minus half x squared. But then we have another term, which is the derivative of this term. এখান থেকে plus minus নামবে, এখানে plus minus already ছিল, so এটা just plus হবে, এবং এখানে হবে হচ্ছে গিয়ে c, এখানে ছিল x n minus 1, এটা হয়ে যাবে x n plus 2, এবং এখানে হবে e to the power plus minus half x squared. Okay, so this is the once again right. So this is psi double prime. So এখানে there are a few things to notice. One is that this has the same power of x as this. So we can, so এখানে n, আর এখানে হচ্ছে কি n, so that will become 2n, right? So আমি psi double prime কে লিখতে পারি, we can factor out c, which is everywhere. We can factor out x to the power n plus 2, which is this thing. And we can factor out e plus minus half of x squared. So ব্র্যাকেটের ভিতরে এই টার্মটা থাকবে 1, আর এই টার্ম থেকে হবে হচ্ছে এই টার্ম আর এই টার্ম মিলে হবে হচ্ছে গিয়ে প্লাস মাইনাস 2n plus 1, কিন্তু আমি তো x squared plus 2 outside নিছি, so এখানে এটা it has to be divided by x squared. And then I have to look at this term. এখানে আমার কি থাকবে n minus 1 divided by x to the power 4. Okay, so this is the psi double prime. But you see that we are taking x to be large. This is the fun of asymptotic analysis. X is large, so the leading term will be given by this. Okay. So in that limit, x to be large plus minus infinity, psi prime is actually given by, sorry, no, I'm sorry. It's, yeah, that's true. Yeah, it's given by the first term. So we can, but you see, this equation had an x squared in it, right? So the first term has xn plus 2. So let's just factor out x squared and write the rest of it in, so c, x to the power n, e to the power plus minus half x squared. So voila, you know, this is exactly psi in the, that we, you know, this thing, right? So we have proved that psi double prime is equal to psi, or we can put an equal to sign here because we are taking the limit x goes to infinity, right? So our solution is correct. Okay. Any comment on the any comment on this? So one thing we can do, there were two solutions here. Psi had asymptotically, it was some constant some constant x to the power n e to the power plus minus half of x squared. So here I don't take the positive power, I have to take the negative power. There's a question. Xn plus n আর 2 যোগ করলে xn plus 2 হয়. So I'm just taking x2 out of the bracket, okay? এবং এর ভিতরে xn টা থাকতেছে. Right? So we have to take the negative power because we know that our system is bounded. Right? The particle motion is bounded. আমরা যদি এখানে নেগেটিভ না সাইন নিয়ে পজিটিভ সাইন নিতাম তাহলে psi would blow up at infinity, right? Which is not physical, right? First, it won't be normalizable. Second, it would say that the particle can be found at infinity with overwhelming probability, right? All right. So of these two signs, we take only one sign. Right? So this is the asymptotic analysis. In the next class, we will do an exact analysis, okay? So let's stop here. And let's take any question. So again, asymptotic analysis is telling us that we have a potential like this. Now, if I go all the way to infinity or very large x, right, my wave function should be decaying. And that's why we took this sign, right? For whatever value of n, if n is positive, n is n যতই বড় হোক না কেন, this will always, this decay will always be stronger than that, right? All right, I want to stop here before moving on in the next class. So next class will be probably on I don't think I can do on Monday because I'm traveling on Monday. But I will maybe Tuesday. Yes, sir. Are there any questions? Okay, তোমরা অনেকেই এখানে আসো যারা কোয়ান্টাম 2 এর জন্য এখনো বোধহয় রেজিস্টার করো নাই, তোমরা রেজিস্টার করে ফেলো। বাট আর দু একজন বোধহয় আছে যারা কোয়ান্টাম 3 2 আগে করছো বা 3 নিতে চাচ্ছ অথবা কিছু। যদি ওইটা হয় তাহলে আমাকে ইমেল করো, কারণ কোয়ান্টাম 3 তে আমি কোয়ান্টাম 1 কোয়ান্টাম 2 পাস না করলে কোয়ান্টাম 3 এ ঢোকাবো না, আর কোয়ান্টাম না পাস করলে তুমি কোয়ান্টাম 2 তে আসবে না। আচ্ছা, ডিপার্টমেন্ট চেঞ্জ করার ব্যাপারটা তো আমরা এখানে ডিসকাস করতে চাই না, ঠিক না? ওইটা তুমি লুৎফরের থ্রুতে করো, তুমি লুৎফরকে ইমেল করো, আমাকে কপি করো। আচ্ছা, any other questions relating to this course?
Sir, could you briefly tell us about the books you are using along the semester?
I will post the name of the books here.
Oh, okay. Thanks.
This is from Powell and Cressman, আজকেরটা। তারপর একটা অন্য জায়গা থেকে, কোথা থেকে আমি ঠিক জানি না, কিন্তু অনেক বই আছে, আমি ওই বইগুলির নাম দিব। আমি এখনো সিলেবাস তো দিই নাই, সিলেবাস যখন দিব তখন ওইটা দিয়ে দেবো, ঠিক আছে? ভেরি গুড কোয়েশ্চেন। এইটা Powell and Cressman থেকে, ওকে? সো এটা Powell and Cressman থেকে পড়ো তোমরা, and that's something you need to do. You need to be regular from the very beginning. হ্যাঁ, Powell and Cressman এর ইসের the simple harmonic oscillator is very good. Okay, any other questions? Okay, if not, have a good weekend, and I'll talk to you guys next week. Okay.
Sir, can we get the lecture notes for today in Piazza?
Um, I will give you the video, but the lecture notes will be a few days in coming. Okay.
All right, sir.
Thank you. But if you want the details, look at Paul and Crispin. Okay. Any other questions? Well, in that case, have a good. Any tips for being consistent in studies? Yeah, do it regularly. Do it regularly. Do it smartly. If you get stuck, ask for help. Solve problems. Solve the lecture notes. Work hard. Okay. And come to office hours. I think probably Shafin will be assigned as the TA for this course. Ask Shafin, ask me if you have questions. Okay. Any other questions? Okay, in that case, have a good weekend, huh? Rest of your week.